Good afternoon. We can start. And okay. Let's close our discussion, this chapter on fracture mechanics and especially fatigue. Let me underline two additional items which we skipped last time, that the fatigue behavior of materials are also obviously conditioned by materials properties and essentially by the microstructure of the materials itself. What is going to happen is that at low temperature, grain boundaries can act as a barrier for crack propagation, and this results in a fatigue limit which is a bit higher than those of the same materials, but having small grain microstructures. At that temperature, these grain boundaries can be weakened, as we know, by solid state diffusion. That means diffusion of atoms, which is one of the mechanisms responsible of creep. And so fatigue limit is lower for small grains. Then the grain shape, which is also called texture, can influence fatigue life and can, to some extent, that depends on the grain shape, to lead to some anisotropy in behavior. And inhomogeneities, like, for example, imperfection of the crystal lattice or particles, impurities, small fibers, can have a negative effect, say, if they act as stress concentration points, which can give rise also to cracks initiations, or in some cases, as we have seen in terms of general mechanical behavior and crack propagation inside, for example, ceramic materials, they could be also could have some positive effect if they contribute to stopping the crack propagation or to insert inside the material some dissipation in terms of energy mechanism. So microstructure is very important. Being fixed at the chemical composition of the materials itself, the fatigue life can be sensibly affected by this feature. Also, the environment, the working environment is very important, and this must be remembered since usually, not always, but usually we make fatigue lab testing in a well-defined environment. And the effects of the environment on fatigue life are essentially related to temperature effects and chemical attack, that is chemical reactions, that is corrosion, for example. So if we have very low temperatures, we know that the, let me say, ductile behavior of the materials is a little bit reduced. And this is always said as the material is going to move to a more brittle behavior. Due to the prevention of plastic deformation in the sense that these locations, they do need higher energy level to start movement. At high temperature, typically higher than 50% of the melting temperature, we know that quick deformation can up and can be present, and can be present in the two forms that we know, dislocation movement and, as I told before, diffusion, solid state diffusion. In the case of solid state diffusion, we can remember that we are talking about diffusion of atoms to and from the grain boundaries, and weakening of the grain boundaries due to sliding can have as a result a loss of intergranular adhesion. And so if this happens, fatigue cracks can travel more easily between grains or cross-grain boundaries, and this is a phenomena which is a synergistic effect of creep and fatigue, which is also called as creep fatigue. Very hard to model. Some experimental, let me say, equations they are available, but for specific materials. And the grain boundaries can also be weakened by the environmental interaction, that is chemical influence. For example, just to give to you an example, hydrogen or other gases can diffuse to the grain boundaries, and thus they could, this is the case with hydrogen, reduce the bond strength, and or the other cases in which for example, we have coated, in order to protect our component by environmental interaction, the components itself, and if the protective surfaces film can be cracked, this can be sources of cracks which can then propagate. And so we do have also synergistic effects, not only between creep and fatigue, but also by on corrosion and fatigue. If we move to the crack growth modeling, we can say that all the experiments that have been done up to now, they have shown that if we pay our attention on the crack length, this crack length is a sort of exponential function of the number of cycles, which cycles, the fatigue cycles. And this means that the crack growth during fatigue is very slow till the final stage in the fatigue life, where a very short, a relatively short number of cycles can result in fast growth of the crack itself, leading thus to failure. The initial fatigue crack length, AI, it has a very important, let me say, effect, and is a very important parameter for the whole fatigue life, which is usually denoted as a capital letter N with a pedix F, where F means failure. If we think to start, for example, by using a material which has no damage at the beginning, usually, as in the video that I showed to you for the CT specimens in the last lecture, it is necessary a number of cycles that is usually called the capital letter Ni to initiate a crack by dislocation movement and void coalescence. Remember what we have seen for the crack propagation in ductile materials. And at this fatigue crack initiation life, the initial crack has been formed, but in most cases it's quite small, so it cannot be detected, for example, by non-destructive techniques. This is the stage one, and the crack growth is due essentially to the presence of shear stresses and involves slip on a single crystallographic slip plane. The crack propagation in this starting phase is very, very low in terms of rate, and it typically, not always, but typically, it is lower than 0.25 nanometer per cycle. After this number of cycle N high, which is necessary to initiate a crack when it is not existing, we enter in the so-called stage 2 of crack growth, and the crack propagation is faster. Typically, and again, typically, not exclusively, it is on the order of some micrometers per cycle. And in this case, in this stage, the crack growth is due to the presence of tensile stresses, and involves also, when ductility cannot be neglected at a microscopic scale, plasticity slip on multiple slip planes at the crack tip, where we have the maximum stress concentration. And this gives rise to striations, which can be observed on the typical fracture surface of a component broken by a fatigue cycle. And after a large number of cycles, the cracks can reach a length that we can call it, for example, A1, which can be detected by non-destructive techniques. Remember what we have said many times, but that also in this case, if we are not going to be able to detect any crack at the beginning, at the initial stage, by using non-destructive techniques, for safety, to be sure, we start in any case with an initial crack which is not equal to 0, but is equal to the sensitivity of the NDT techniques which has been used. But generally speaking, then after this, the crack growth is much faster. And after the fatigue life and F, that is the failure number of cycle, the total length has reached the critical length, which is the length of the crack for which we are going to have a stress intensity factor which is higher than the fracture toughness of the materials itself. And obviously, if we have loading showing higher amplitudes, the crack growth will be faster. Then after a certain number n of cycles, if we say that after this number of cycles, we have not reached yet the failure, this means that we have a residual life. And this residual life, which is the number of cycles necessary to reach the NF, that is the real number of cycle, is called also as NR with predix R, which stands for the rest life of the absolute materials, even though usually the rest life is defined by the ratio between NR, the residual cycles, which can be tolerated by the materials itself after N cycles, and the number of cycles requested to have failure of the component. It is blocked, no, okay. So we have this sort of diagrams in which you see we can have the stages we have discussed, we can have the growth of the crack length with the number of cycles. We reach the failure cycles essentially when we have reached the critical crack length, and we define the rest life like the ratio between NR and NF, which is obviously equal also to 1 minus the effective number of cycles which has been made divided by the failure number of cycles, depending obviously on the applied stress. And so the crack growth model, which can be used to predict the fatigue life with a micromechanical approach, essentially they aim to define a relationship between the crack growth rate, which is the derivative of the crack length with respect to the number of cycles, let me say with a link with the amplitude of the fatigue cycles or with a maximum load, to speak generally, which can be expressed, obviously, the amplitude of the maximum load by using the stress intensity factor, since the crack is going to propagate itself starting from the more stressed area, which is located at the crack tip. We assume now to be in the condition of a high cycle fatigue regime, where generally speaking, the stresses are low, the yielding strength, but stresses can be higher than the yielding strengths. Just remember the elastoplastic simplified fracture mechanical models at the crack tip. And the microstructural models, they relate the crack growth rate to microstructural parameters, such, for example, the spacing between the observed striations on the fracture surface. And for certain materials, it has been found that this spacing in the striations is something about let me say, 6 times the value given by the variation due to the variation of stresses of the stress intensity factor associated to the cycle of fatigue divided by the Young modulus of the materials itself with an exponent of 2. Why we are going to use the Young modulus? Because if we are talking about low stresses, we can make an initial assumption on overall materials, with the exception of the crack tip, that we are in a sort of linear elastic behavior. But in any case, we do have available, and they work well, some phenomenological models which are formulated, which have been developed by fitting experimental data of crack growth on the specific and applied fatigue conditions. And these relationships, they describe the crack growth rate, the derivative of the crack length with respect to the derivative of the number of cycles, as a function of the stress and as a function of the crack length. And there is a very well-known relationship, which is, let me say, known as the Paris law, and then which we have seen some years ago, which, let me say, refers to the application of linear elastic fracture mechanics to this kind of phenomena. And the Paris law is based essentially on 2 parameters, a coefficient C and an exponent M, being the value of delta K known when we know the applied fatigue cycle, because we know the value of the maximum stress, the value of the minimum stress of the fatigue cycle, and then we are able, with our model, to calculate the stress intensity factor for the highest stress and the stress intensity factor for the lowest stress. Just remember, because we discussed this again in the other courses, that when we are going to apply, then we will see other limitation, the Paris law, and we are going to use the delta K value inside this very simple formula, we need to neglect the compressive part of the fatigue cycle. That is, if the minimum value of the applied stress on the fatigue cycle is lower than 0, we need to use as a value 0. That means that the minimum value of the stress intensity factor, in this case, when the minimum stress is a compressive stress, becomes 0. The Paris law was essentially, let me say, published in the 60s, and it is still widely used. The parameters can be estimated and calculated by fitting the experimental data, and the procedure is quite simple, because if we use a double logarithmic axis in which we put on the y-axis the logarithm of the crack growth rate, and on the x-axis the logarithm of delta K, this simple law, as you can see here by the formula reported, becomes a straight line. And so by calculating the slope of the interpolating straight line, we can have the exponent M, as well as, if we are going to look to the intersection of the straight line with the y axis, we can we are able to calculate the constant C, and thus we can use this formula for our evaluation, numerical evaluations. It has a limit, because for low and for high value, that is, we are going to put our attention to the extremes, the law, which has been formulated by Paris, is not able to describe the crack growth rate with accuracy. And when the value of delta K is, let me say, near to the threshold value, K threshold or delta K threshold, that is the lower limit, generally speaking, a crack grows very slowly. And it is hampered by the roughness of the crack phases. For still smaller value of delta K, the crack growth is extremely small, but not completely zero. And then for high values, the other extremes of delta K, crack growth is much faster than the value which are predicted by the Paris law. That is when we are going to approach the critical value of the fracture toughness of the materials. Paris laws essentially underestimates the crack growth rate. We know parameters, and this is just an example for you of the most common materials, so we do not need to make experimental testing for the most common materials. Otherwise, we can use the procedures that we have just discussed to have an idea of which are the value of the two constants, C, M, and also of the delta K of threshold. Pay attention, and this is just reported for you, on the dimension of the constant C, which depends on the value of M, and thus the conversion of units when it is needed must be done with accuracy and with care. And some is one example of the conversion from British standard, which are quite common, to international system units and vice versa, are reported here just for your remind. We can use our derivative equations, and we can make an integral of that simple derivative equations, putting as extremes when we are going to make the integral on the crack length, the initial, you see here, AI crack length, till the final crack length, which is the critical crack length, and at the same time making the integral, the number of cycles starts from Ni, that this is the initial number of cycles which are necessary to have AI, or from 0 if we are going to make the hypothesis that AI working in safety is existing already inside the materials, to the number of cycle of failure. And that's quite simple. This expression is an expression in which you see you have beta. This beta is just the shape factor, the geometry factor epsilon that we have in the formulation, in the general formulation of the stress intensity factor. So that if we know the value of Ni, which could be also 0, we know the initial crack length, the critical crack length, which can be easily calculated since the maximum stress of the fatigue cycle is constant. And thus, if we know the fracture toughness of the materials by using the fracture mechanics approach, we can calculate the value of the critical crack length, knowing the geometry factor epsilon beta here for the definition of the stress intensity factor, knowing the two constants C and M by table like this or by experimental values, knowing the value of the amplitude of the fatigue cycle, we are able to make a prediction of on the number of cycles which are requested in order to work to have a failure of the materials itself for that cycle. This is not the only model is one of the most used, but there are many other models which have been proposed which can be used in order to have an estimation of the fatigue life when we do have, like in this hypothesis, an harmonic fatigue cycle applied. You see here, I have reported for your knowledge the Erdogan, the broken sheave, Foreman. Now they were developed in different time scale, but they all are going to refer or to give to us an expression of the crack growth rate linked to the fatigue psych properties. Here the meaning are those we have already discussed. Beta is again epsilon, that is the geometry factor in the definition and the general formula of the stress intensity factor. C and N and M, in this case, we do have two exponents, two parameters, M and N plus C. K1C is in mode 1, the fracture toughness of the materials. Delta K threshold is the delta K that we have seen on this graph here, the threshold. And then we have beta in this case, which has a meaning different from those reported here, because it's estimated and evaluated by using this ratio. Sum of the maximum and minimum value of the stress intensity factor and divided by the difference, by max minus the minimum. Here you have other expressions, but you see the meaning are all the same. Other models which were then developed later on are these: the Workel model, the Priedel model, the McEbly model, in which also some other parameters related to the materials are put inside. Here, the stress reported is the yielding stress of the materials. Instead, this constant R, A, is something a little bit difficult because it's related to dislocation movement, to the influence of the environment, but they are obtained experimentally. And one of the last is the model developed in the Flagro program by NASA, 89, which is a sort of a generalized model, as you can see here, in which we can have the possibility, depending on the value of the exponent, for example, here reported, here you see we have three exponents, M, N, A, P, and 4 and Q. Depending on the value, this model can degenerate, that is a more general model, can include the Paris, the Foreman, and the Walker model, which are essentially the most used in the micromechanical approach to fatigue problem. All this is related to the high cycle fatigue. That is, we have made the hypothesis that the stresses are not so high, I mean, in any case lower than the yielding stress of the materials. And the Paris law and also the other expressions that I have showed to you, they can be used if this hypothesis, that is the high cycle fatigue regime, is satisfied. But we do have also low cycle fatigue, as we have defined, when the stresses are higher. And in this case, that the equations cannot be used anymore. In this case, we have let me say, large plastic crack tips regions. Models, refined models, are still under development. Here, just for you, I have presented one model for crack on the under multimode fatigue loading, but please remember that this is an extreme case. So obviously research and development is going ahead also in the case of low cycle fatigue. But for us as designer, as engineering, we usually put our components in a way to work for which if we do have fatigue problem, we can have only high cycle fatigue problem, because this means that the fatigue life of the component itself is, for that case, let me say, the maximum possible. And we do not pay too much attention on these causes, on the sophisticated modeling of low cycle fatigue, since you will ask it to be used in your profession only essentially high cycle fatigue regime, unless you enter the research and development area into material science. You see here another possibility, and just to complete our link, is to make modeling of fatigue in the case of low cycle fatigue by referring to the J integral that we have defined by talking about the generalized approach of fracture mechanics, including the most sophisticated, let me say, approaches for elastoplastic fracture mechanics. All what we have seen and what we have said up to now is referred to a special case, that is the case in which we have just harmonic loads, that means a fatigue cycle, one fatigue cycle, which is characterized by a constant frequency and a constant amplitude. These are the further assumptions which can be must be satisfied to use at a glance at the beginning the modeling that we have formula that we have seen before. But if we move to practical situations, these hypotheses or such kind of loads will almost never be matched, will almost never be seen. And both loading frequency and amplitude will generally vary over time. In this case, when we do have a cycle loading, which is again under the fatigue hat, it belongs to the fatigue world, we say also that when cycle loading with a time-dependent character in terms of frequency, in terms of amplitude, is called as a load spectrum. So we need to make a little bit of refinement in this in order to move to something which is more simple, is more responded to real working conditions. Let's assume that the direction of the loads remain the same, and let's assume, for example, that we do have a load spectrum which is a mix of harmonic loads, as reported here in the picture. For example, in this case, we do have 4 harmonic loads. You see let me use my pen. You see, this is the first one, this is the second one, and so on, having in any case different frequencies and different amplitudes. We usually denote these harmonic loads with Ni, that means small letter, not capital letter I, that is the number of cycle, and small, which is related to the 1 conditions, and 2, the number of cycle, which is related to the 2 condition, and so on, depending on the sequence of the various harmonic loads we need to model. And for each individual harmonic load, the lifetime is supposed to be known, and we can call it NIF. Why? because this is the most simple case. And so in the most simple cases in which we do not have any variation of frequency and amplitude, we have available, for example, experimental data which tell to us, remember to the Bowler curve, which is in that condition the number of cycle for failure. So we suppose, but this is really true, that NIF aesthetics is a quantity which is known. This problem was studied by Miner in 1945, and this scientist found during his studies that the fatigue life for the whole spectrum, that is, in the case we have a sequence of harmonic loadings, is not dependent on the sequence itself of the individual loadings. That means if we have, for example, here, just to have an example, the failure of our component, well, this failure, the total number of cycles for failure, does not change if we, in our sequence, have as 4 cycles, the cycle number 2, then the cycle number 1, and so on. And this means that the individual harmonic loadings do not influence the damage growth. Damage growth means the crack growth in the following loading stage with a different character, with different properties, with a different frequency, with a different amplitude. In any case, the final lifetime of our component can be considered as a value which is reached when the summation of the ratio between the number of cycles for the I conditions divided by the failure number of cycles for the I condition becomes equal to 1. This is the hypothesis which has been made by Miner. And this is called also the Miner's rules, which is approximately valid for a wide range of materials, even though in some cases we do have a, let me say, the ultimate sum of all these ratios, which can vary between 0.6 and 2. But for this special case, we know, and in the literature and the specialized books, that we need to refer not to 1. In case we do have values which are different from 1, that is, for example, in the range 0.6 and 2.0, this means that really the hypothesis of no influence or no interaction between the different load cycles is not fully respected. But generally, the Miner's rules is written in this way. And when we write this, knowing all the values of the failure number of cycles for the I conditions, we can treat the problem of the presence of a load spectrum, okay? Because the sum 1 means failure of the component, like it is reported in this example, where we do have, after the 4th cycle, this residual life, etc., etc. When the residual life, that's the same approach, becomes 0, that means that we have reached the failure of the component. If we want to make a little bit more complicated this approach, there is that we can say that although the load spectrum is something which is more realistic with respect to the harmonic loading case, having a constant frequency and a constant amplitude, looking to let me say real application, we should also add that there are that practical loading are in most of cases random, as it is illustrated in this picture. And we can predict fatigue life when we are in presence of random load only if, by using, for example, the Miner rules, this random load is transformed, is transferred into a load spectrum, that is onto something which can be modelized like in this way. And there are many mathematical methods which allow to us to make these transformations. There are many counting procedures which are based, for example, about the peak count, the range pair count, the rainfall count techniques. But by mathematical modeling, we are able to transform this random load in something which is very similar to a sequence of harmonic loadings, thus allowing to us to use the equations that we have seen. We can also have, obviously, let me say, experimental evidence of these random loads and then treat it in order to transform in a sequence of harmonic loadings. And just some example, for example, of measured, let me say, frequencies and random cycles applied here to a machine, here to a sea vessel, here to an airplane. As you can see, you have various phases of a flight, including also the possibility to have turbulence, having landing, and all the other phases of a flight, and thus using this mathematical approach, which are problem of numerical analysis of signals, we are able to come back to this situation, that is to deceleration, and that is the possibility to predict fatigue life. Some additional concept which could be met in your professional life, that is, which for these reasons they are worthwhile to be mentioned, are related, for example, to the existence, possible existence of overloads. In this case, let us discuss, obviously, on the worrying situation of tensile overloads. And the question is how, if overloads, which is a phenomena sometimes common in the exercise of structural components, how overloads can affect, or if they affect, the fatigue life. Let me say our common thought, our feeling as written here, is that overloads, they should be something bad. But, and this is one of the reasons, because of, if the conditions that I will show to you, they are met, we can also, let me say, neglect that. The practical experience shows that usually crack propagation is slowed down, that is, the rate is lower, by the existence of such an overload, at least during a limited number of cycles. So overload means that we have a maximum value of the stress intensity factor, which is let me say, constant or variable, depending in the case of random loadings. And then we have, for some working reasons, a value of the maximum stress intensity factor related to the overload, which is higher than the maximum of the maximum, would say, of the random loadings transformed then in a sequence of harmonic loadings. And this crack retardation, at least at the beginning, can be explained by thinking, by discussing on the stress state in a region which is in front, that is near the crack tip. As it is shown in these figures. This is the crack tip, you see. This is our model. This is the yielding strengths of the materials, our model of a full elastoplastic simplified, as we have discussed with the fracture mechanics. And you see here, this is the x-axis in which we do have sigma xx stresses, and the y stress axis in which we do have the sigma y stress as we have defined with studying the stress modeling at the crack tip for the fracture mechanics. The figures which is reported here tell to us that if the loading stress is increased like this to a maximum value sigma 1, representing our overload, and then it decreases again, going to 0 when the overload is 0 and we have just the random load, in a point A and a point A and B, which are near the crack tip, we can have the stress plotted as in the figures. And what is going to happen is that if this overload is able to increase sensibly the plastic response of the materials, this can happen, for example, exactly near the crack tip, whilst a little bit far from the crack tip, due to the stress concentration we do have here, the material's behavior still remains elastic. So after unloading, the strain in these two materials, point A and B, are more or less the same. And this gives rise to a compressive residual stress in the point A, that is in the area which is most stressed at the crack tip. And this compressive residual stress can inhibit or can make slower the opening of the crack, and thus giving a sort of retard effect. And we do have also, they have been developed quite recently, some models in which, for example, Willenborg has published a relation for the stress intensity factor, now called KR, in the crack retardation stage, in order to take into account what we have just said, and answered also by other researchers, in which the relationships are taking into account the influence of this compressive stress zone at the front of the crack tip. This is one example, but we do have also other examples like this, Johnson, which was a refinement of the previous model, or others like this one developed by other scientists. With applicable, usable, even though some conditions are respected. Remember this meaning of R. The meaning of R is the ratio between the two values of the stress intensity factor, which are linked to the fatigue life cycle. So this just to tell to you that, let me say, at least at the initial phase of crack propagation, the presence of overloads are not so severe, because we can experience a lower value of crack propagation of the cracks itself, and thus if we neglect for a preliminary design this, obviously having assumed that these overloads is not able to put all our materials in a plastic deformation, we are authorized to use the most simple models, even though some experience and modeling have been made also in this case. Now to close, we need to make some refinement, as I anticipated to you last time, on the class, a special class of materials which are ceramic materials, that is, materials which are brittle in behavior. Talking about fatigue, not talking about fracture mechanics, because remember that the general approach, that is the linear, the initial better approach, that is the linear elastic fracture mechanic models, they were developed for brittle materials. Then we have made some variation in order to use these models also in the case of a small scale yielding, that is a small elastoblastic behavior of the material itself. But when we, as I told to you last time, when we some years ago started to discuss about fatigue, and we were limited in our approach only to the use of the Paris law, and this is the reason because we now have made some additional consideration in order to let you know also other models, including the NASA one, which can be used for fatigue prediction of metallic alloys. We said, well, if we have in front of us a brittle material, we can apply the concept of fracture mechanics, but we can assume this was we said some years ago, that the fatigue life of the brittle material is equal to 0. Well, this is not pure, this is not true. The brittle materials, they do have a very limited, if you want, fracture number of cycles in order to gain fracture, to have failure, but really and correctly speaking, the fatigue resistance is not always 0. And fatigue crack advance in ceramic materials is conceptually different from that which is going to occur in metallic alloys. And to explain this, we can involve the concept of intrinsic and extrinsic, let me say, behavior, because there are essentially two possible classes of fatigue mechanism, where failure is associated with the biggest, with the dominant crack. These two, let me say, mechanisms are: the first one, the so-called intrinsic mechanism, where, like it happens in metals, the crack develops or advances in length by damage processes, which are going to be developed, as we have just discussed up to now, in the crack tip region. But there are also, generally speaking, extrinsic mechanism, where the crack advance mechanism ahead of the crack tip is identical to that for monotonic loading, that is harmonic loading, but the unloading cycle promotes an accelerated crack growth by degrading the degree of crack tip shielding behind the tip in terms of stress, obviously. And in metal fatigue, that is in the cycle processes in metal fatigue, the mechanism, the intrinsic mechanism is the most important, is predominant. Whilst if we talk about brittle materials, the cycle fatigue processes in ceramics are essentially extrinsic. And the mechanism by which the crack advances is thus identical under cycle loading as it would be in a single overload cycle. And this clearly is consistent with the dependence of the growth rate on the maximum value of the stress intensity factor for what it concerns the ceramic or the brittle materials, rather than on the difference between the maximum and the minimum value of the stress intensity factor, as we have seen in the Paris law and as we have seen also on the other equations which can allow us to model. And there is also for this with the dependence of the essentially or mainly on the maximum value of the stress intensity factor, similarity in the fracture surface appearance under cycling and under monotonic loading. These are an example by a picture which are, let me say, extrinsic and intrinsic mechanism, for example, by referring to toughening, as we have already essentially discussed. for example, when we have seen the behavior in terms of crack propagation qualitatively for ceramic matrix composites. So we can have grain bridging, fiber bridging, we can have cleavage, microvoid coalescence. I had a crack tip essentially for what it concerns the metallic alloys. Otherwise, for the brittle, the behind crack tip, that is the extrinsic toughening, the extrinsic phenomena are the most important. No difference, let me say, when we talk about brittle materials, about the, for example, the way to represent the results which put in relationship the crack growth rate with the stress intensity factor. We can have, but the shape, as we will see, will be a little bit different. Again, the three stages, that is the regime A, based on non-continuous mechanics, where we do have a large influence of microstructural mean stress environment. The B, which is the area in which, for, as you can see here, for metallic alloys, we can use the Paris law, excluding, as we have said, the initial part and the final part where the Paris law is going to underestimate the crack propagation rate. But we have to say that then we will see also the graphs referred to this phenomena, that due to this extrinsic predominant mechanism of fatigue in brittle materials, we can have various forms depending on the prevailing shielding mechanism. And we can have, for example, sudden premature fatigue failure on metallic reinforcement phase in ductile phase toughness materials, as well as, for example, effects of fiber bridging, as we have seen in the previous picture. We do have also another important concept, which usually is used when extrinsic mechanisms are prevailing, and it is referred to the so-called R-carb toughening. Let us explain to us what is R-carb toughening, and so you will be more aware, because we discussed the energetic approach to fracture mechanics. Generally, and this is what we said when we discussed the Griffith theory, essentially, defining the strain energy release rate and the critical value of the strain energy release rate, we have said that by using the energetic approach in linear elastic fracture mechanics, the crack propagation is going to happen when the value of G, the strain energy release rate, is higher than the critical value. Let's call it in this way GR, for example, which is the material's resistance to crack propagation, to crack extension. And at any moment in which the value of G is higher than the critical value, the crack extension is energetically favorable, because this means that we do have an energy which is released by advance of the fracture itself, higher than those which is requested, to create new surfaces. But a complication, this happens essentially when we do have materials in which extrinsic phenomena are going to condition the fatigue behavior, is that in some of them, the critical value, GR, is not a constant value during the crack extension process. And we can have, for example, three different behavior. The standard one, in which we do not have any dependence. We can have a case in which the value is going to rise like in the green curve, or the case in which the value is going to fall. Here, please note that we have reported with respect to the value at the initial stage, the ratio between the critical strain energy release rate during crack propagation refer to the initial conditions, which is related to the initial size of the effect. Well, this curve, when reported, and each material has its own, and they are quite important in brittle materials, they are called also crack growth resistance curve or air curves. And this is another concept important, which can be also converted, since we have seen the relationship between the strain energy release rate and the fracture toughness. It can be also converted in terms of stress intensity factor, but usually is explained by looking to the energetic approach. Here you have reported some of the extrinsic mechanisms, which are most important for materials with brittle behavior. We have discussed that crack deflection, microcrack toughening, transformation toughening, think for example to zirconia, brittle fiber whisk toughening in the case of composite materials. There is also the possibility to insert inside, let me say, brittle materials, ductile particles. In this case, we can have extrinsic phenomena which are called ductile particle toughening. And the effect of these extrinsic mechanism is, let me say, to contrast, not to impede, to contrast the crack extension by mechanical, microstructural, environmental factors that locally can reduce the near tip stress intensity. That is to promote air curve toughening. That means to promote an increase of the air value of the resistance, moving towards a situation which is the green here. And this is reported here, for example, in the case of zirconia. We have discussed it many times, so I want not to repeat again. Just remember that we start for partially stabilized zirconia from some units of megapascal per square meter in terms of fracture toughness up to something which is approaching also 15 megapascal per square meter when we do have phase transformation due to the presence in partially stabilized zirconia of metastable phases. Here you have just, let me say, a representation on how the fractures and phases more or less are the same under monotonic loading and under fatigue loading for what it concerns brittle materials. These are some examples of, you see, of fatigue behavior of ceramic-based material. So you will see we do not have a straight line like this. That means infinite value of crack growth rate. That means no resistance to fatigue. We do have a slope. It is a very, let me say, high slope, near to 90 degrees, but it is not a straight line. And so this means that also brittle materials, and obviously if we have toughening, the resistance is higher, can be modeled for very short time. That it means they request very reduced number of cycles to get failure, but can be modeled with some equations which are not so far from those we have defined for the metallic alloys. And that's the basic equations that we can have in mind, and which is the most common used to model crack propagation of crack, okay, of defects inside ceramic brittle materials subjected to fatigue loading, as you can see, we do have again a parameter, which is the crack growth rate, like in the formula we have seen before, and we do have again values which are referred to the stress concentration. We do have the stress intensity factor difference, but you see here the basic equations, as we said before, keeps into account in an explicit way the maximum value of the stress intensity factor. If we want to compare these equations with the basic Paris equation that we have seen, we could say that this constant C1 is essentially equal to the multiplication of the Paris constant C per 1 minus R, where R, remember, is the ratio that we have already defined before between the minimum value of the stress intensity factor and the maximum value of the stress intensity factor. This is for positive value of R, that means for positive value of stress, that means for tensile stress, with the exponent N, and the sum of these two exponents, N and P, is substantially equal to the M exponent which we do have in the Paris law. What is going to be different, just an example here. For example, if we have, this is a case of composite materials, but short fiber reinforced, but it doesn't matter. Have a look here that for this kind of alumina-based material, ceramic-based materials on alumina, that's a brittle ceramic materials, the values of the two exponents N and P are respectively something very near to 10 and something very near to 5. If we use this same approach, for example, for a nickel-based superalloy, well, we find the values of the exponent which are very lower, 0.5 for N and 3 for P. This would mean in the classical Paris law, that for a nickel-based superalloys, the value of the exponent M would be near 3.5. In the case of ceramic reinforced like this, ceramic matrix, ceramic reinforced ceramic matrix, because this is a ceramic matrix composites, we can expect value of the exponent M, which are something around 15, that is 5 times higher than those of nickel-based superalloys. So the crack propagations gives to us lower number of cycles with the same applied to failure, with the same applied stress, but not zero. And so for some special application, as those I mentioned to you on the last time, for example, flying object with very high speed, we have available tools in order to have a prediction of the fatigue resistance. But if the emission time saves something of the order of how to say, minutes, 10 minutes, some 10 minutes, obviously we are not talking about classical fatigue or metallic alloys, but we can expect that they are able to be designed in order to resist for the emission time for which they are requested. Here, just to conclude, you have also, let me say, a sort of comparisons. In the case we would like to use the general formulation we have seen here, all for metals, also intermetallics, they do have other approaches, and ceramic materials with the meaning of a K max threshold and K0 that we have seen before. See here for the metals, P is very sensible higher than N, and this means that this can be, for the simple formulation, neglected, and this means that we have the Paris law. That's not the case of ceramics, but is not only the case, is not the case of intermetallic materials. We have studied intermetallic materials for which the formulation in which the dependence by the maximum value of the stress intensity factor of the fatigue cycle cannot be neglected, since it has a very relevant influence. This for what it concerns the fatigue, and so let's start in the next 5 minutes, 10 minutes, sorry, another topic which is very important for you and for the high-tech application which are underlined, and which is related to the surface engineering techniques. Let me change the presentation so that we can start to discuss about this. Okay, so now I must share the screen. Okay. So let's start this topic, very important, which is surface engineering. We also on this topic have said something some years ago, just some basic concept. Now is the case to treat it more deeply, because this is a very important, let me say in this way, very important set of tools for high-tech engineers. Surface engineering. So we are dealing with the surfaces of components. And when we talk about surfaces of components, surfaces can have different functions, and thus can be asked to have by the designers different functions. So it, let me say, it starts the needs to engineering the surface. Which are these functions? Just basically, they can have the act as a primary function. That is, what is under the surface is something which must show to us the surface properties, okay? Or it can act as protection of the component, for example. Or it can have different properties that, depending on, with respect to the bulk, what is under the surface, depending on processing, treatment, or resulting behavior in service. Primary function, where surface is very important in terms of function which is given to the component. Think, for example, to a telescope mirror. The primary function of the surface is that it has to be reflective, and the rest of the material is a sort of support and give also the shape. Or, for example, in brake pads. In this case, the primary function of the surface is to have a high friction and low wear over a wide temperature range. And then there is also secondary properties of the function to maintain the right shape, but the primary function is given by the surface of the components instead that the bulk of the component. The same applies, for example, for machine tools, as examples, where we want to have surfaces with high hardness, high abrasion, and high oxidation resistance to enhance the lifetime of our machine tools. Or also, just to give another example, in the electronic field, the semiconductor substrates, where we need absolute smoothness and freedom from defects in order to have the desired answer of the semiconductor itself. In terms of protection, instead, in terms of protection, for example, our surface must confer corrosion resistance behavior, and this open, for example, to all the field of corrosion resistant coatings, or must, for example, let me say, have a smoothness defined in order to diminish the problems which are related, for example, to crack propagations, for example, to crack propagation for fatigue. Remember that when we remember some of the fatigue, let's say, influencing factors, the roughness of the surfaces is very important, because higher is the roughness, more easy, let me say, is the possibility to find defects which can undergo other propagations. And if we have the third area, that is the possibility to have a surface state which is different from the bulk as a result of processing of service, think, for example, to the formation of passivation oxides and on steels. Just to give you an example to you, the possibility to have corrosion phenomena localized on the surface itself, and on all what is going to result by using machining, grinding, or polishing processes on the components, that is on the surface of the components. And the possibility to confer to a surface of a component specific function is one of the most important and interesting solutions for engineers when the lifetime of our component is strongly conditioned by the surface properties rather than by the bulk properties. And this also is very important for us, because most of time, and you cannot neglect this, we can define engineering solutions well performing, that is, well matching the expected lifetime, by reducing, for example, the component cost. And the cost is one of the factors which can never, this was underlined to you, be neglected in our applications. I want just to give to you one example, conceptually speaking, and then we will stop for today, and we'll continue the discussion the next lecture of Friday. Think, for example, like in this picture, to a steel fence, which must resist, because that's our design requirement, to atmospheric corrosion. Well, let's talk about, in this case, to the possibility, as it is usual, not to use metallic alloys, not wood metallic alloys. Well, we have on the table two options. One option is to say, I want to reduce, I want to limit this atmospheric corrosion, which is able to affect negatively the lifetime of our fans. First option is to select as a base materials stainless steel. Why? Because we know that stainless steels is a highly alloyed steels, having, as I remember to you before, in the formulation, for example, chromium, having a minimum, by definition, 12% of free chromium. This free chromium is has a high affinity with oxygen, can form on the surface of our furnace a very thin chromium oxide layer. It's very thin, and it is transparent to the light, so we are not able to see it, because it is of some, let me say, 100 of nanometers, not more, but it is on the surface. And this stainless steel, being so we call it in this way, passivated by the presence of chromium oxide, does not undergo to any form, except the case of chloride ions, but this is a, let me say, a subcase, does not undergo to any form of atmospheric corrosion, because atmospheric corrosion is a corrosion phenomena based on the electrical charges exchanges. And if we put a chromium oxide layer on the surface of our furnace, that is a ceramic materials which is not electrical conductive, and thus the so-called electrochemical corrosion will not occur. But this would be just looking to the material selection, let me say, one very good choice. But what are the drawbacks? Well, with respect to conventional steel, carbon steels, stainless steels are very expensive. Then they do have also some other drawbacks. They are difficult to weld. Remember the heat affected zones, for example. They can be difficult, that depends on the steels, to shape in complex form. They need, in order to put on the table, let me say, some, when it is necessary, repairing option, specialized operators. And so this means that all this positive behavior that we have here, responding to our design criteria, well, they are a little bit in contrast with the drawbacks, which if we could have, or if we have on our table another solutions, they could be eliminated. And which could be another solution? Another solution could be the selection of a common carbon steels, which has a low cost, so economy, which is easy to build and to repair, also in complex shape, but which is the drawbacks that we do not have a resistance to corrosion, to atmospheric corrosion. And thus, we can think to combine our concept to modify the surface of the carbon steels, of the carbon steels elements which are used to fabricate our furnace, in order to have the response of good, very good resistance to atmospheric corrosion, just modifying surface properties. And this, for example, can be done by using coatings. Common coatings are paints, which have the, let me say, function to protect from rust. Rust is resulting from atmospheric corrosion. And so of these two options, if we make an analysis, a cost analysis, most of times, this is, from an engineering point of view, the best option. And this means, just to give to you a very, very limited example, but we will see later on, that the surface engineering methods, the technologies that we can have available to modify surface properties, in the case properties must show a primary function, and etc., they are very relevant for any engineering working in the engineering field. And so they must be to some way managed. Other example here, not in the aerospace field, automotive PVD projector, it is made by base materials which is very easy to be processed, for example, by injection molding, so it can be processed in complex shape. It can be light because it's polycarbonate, it's a polymer. It has low cost in high volume production rates, but it has not the reflectivity which is requested for this kind of component. And so what we can do, we could use, for example, metallic materials to fabricate this PVD projection, not PVD, this projector, like, let me say, bulk aluminum, but the cost will be higher, and the system would be would have a weight higher, and so we can arrange the use of a bulk materials polycarbonate polymer, on which, on the surface, we are going to put a coating. In this case, we will see it is a physical vapor deposition coating, in order to achieve the reflectivity value, which is requested for this application. And this can be achieved, for example, by using a coating, that is, by using surface engineering technology to coat these polymeric-based materials with a very small thickness, just 1 micrometer, thus combining the reflectivity properties of the aluminum alloys with the positive feature in terms of facility of fabrications, cost, and lightness of the base polymeric materials. Having said that, and before entering to some general concept of surface, it will be a summary for you, because then we have to discuss about technologies. I think that for today we can stop, and we will start from this slide in the next meeting, which will be next Friday. So I close my video sharing. If you have any questions, please. That seems not the case, so see you again on next Friday. Bye bye to all. Arrivederci.
Arrivederci.
Arrivederci, arrivederci.